Hey everyone, so we have another AMC 8 problem. So this was a number 25, which is the last question. So even though this question can be done multiple different ways, especially like casework might be the good one. But if you kind of increase the number of like the leaves or number of hops, then the casework will be a bit challenging. So which is why I'm not gonna use the casework. So you can just try that on your own just to see how we can do that. But instead, I'm going to introduce something we call states to do this problem, because if you have like more hops than four, maybe 10 hops, or maybe if you have like 10 leaves, so the casework is not really efficient. So which is why the states approach would be way better. So which is why I'll just go ahead and do that. That's the one reason. And the second kind of reminder I like to make, this is a question was given as a last problem, and but if you look at the AMC 10, 12, even AME problem in the past, there were a lot of similar questions to these. But the question now is given AMC 8. So meaning that like if you kind of look for some other questions from the AMC 10, 12, even AME, similar to these guys, a bit like more steps and involved, it's better to do those kind of questions as well, just to feel you really grasp the whole concept of the states approach. And that's one thing. And the second, especially if you are like aiming for like I don't know over 20s on the AMC, then this is something you really need to kind of know more than just the basic tools. So the states might be one of the things that you should actually aim for to get better. So that is something I like to remind. That's why if you have no background about the states, if you never heard, if you never like learned, so please take a look at the resource I will attach in the descriptions and see if that helps. Okay. So anyway, so let's get started with the problem and see how we can actually use the states in this question. So like we are told the cricket randomly hops between those four leaves, each turn hopping into one of the other three leaves with equal probability. So which is nicer. So this may not be the case in all ways, so if this was an equal probability, then we could still do the our question with the states anyway. But in this case, it's equal probability, which is easier. After the four hops, what is the probability that the cricket will be actually going back to the original, like the list that started? Okay, so that's the question. So in this position, like when we say the state, we just talk about like the position of the cricket basically. So like the cricket could be on this leaf or one of the other three leaves. There is no real difference between these three. So it could be one of those three, which is why I'm going to have only two states in this problem. And then one of the most challenging part of the state approach is actually finding out all the different states. In this problem, I will say we have only two states. You are going to be either on the original like leave or in one of the other three. So you have only two possible the state in our case. I'm going to say, let's say this is A. Okay, I'm going to say this is not A. And then this is not A. And then this is not A. So for this for that reason, I'm going to make a state diagram including A, which is our one of the states, and the another state which is not A. So we have only two states in this problem. So how this is going to be looked for? Like when we start on this leave, then there is no choice other than going to one of those three not A states, which means we have a 100% probability that we are going to ending at one of these three not A states. So which is why I'm going to say probability will be 100%, which is 1. Okay, but if we are in one of these three not A state, then you may just go back to A, or you can go like one of the other two leaves that is not A. So which is why we may go back to A, which is like if you are, let's say your first hop is on this leaf, then if you want to go back, so you have three options. So the A is one of those three. Since there is equal probability, so we have 1/3 option, the one-third like chance that we can go back to A. Or if we were at this leave, then there are two other ones that is also not A. So we had two-third like possibility that we could have just ended another not A, which is why I will say this is two-third. And this diagram is called state diagram, which is going to be useful for writing the equation. So I hope that was clear so far. So again, as soon as we have this state diagram, which you don't need in general, especially if you really know what you are doing, but in this case, it's good to see how that looks like. And I'm going to say two more things now. So I'm going to name P of n as the probability, okay, of ending, ending at A after n hops, okay. So what does that mean? Like if you are asking what is P of 0, which means what is your probability of being at just the leave A, right? So that's gonna be after 0 second if you are looking for P of 0, and P of 4 is what we are interested because we are looking for the like 4 hops after. So and then I'm gonna call Q of n is the probability of ending at not A. Okay, so after n hops. So if this is the case, you know, since we have only either option, either you're gonna be at like at A or not at A. So when you add those two probabilities, so P of n plus Q of n should be 1 because that's total case, right? So this is gonna be useful. After this moment now, I can just make a nice table just to find what I am looking for. So, which you don't really need, but it's kind of good to have organized way. And if you do say, let's say this is like P of n, and then this is Q of n, and 0, 1, 2, 3, 4. So this is what we are looking for. So we are going to find the value of this. And so now let's find the each information. And also another thing that we need to remember is our like the original like cases, which is like probably at 0. Like at the beginning, we were at this like leave, right? So that means before we start hopping, we were there 100%, meaning that P of 0 is 1. So P like Q of 0 has to be 0 because we were here, not one of the other three. So which is why this is 1, this is 0. That's our initial condition. And without really kind of writing the equation, we may find this second immediately, but let me write the equation before we move on to that guy. So again, if we want to get the P of n, so n is just the probability of ending at this state after n seconds. So only way that will be happening if you were at not A, and then 1/3 possibility that you are going to be ending at A. So which is why P of n equals 1/3 times Q of n minus 1. N minus 1 is just the previous second. So like if you are ending at one of these three locations, and then 1/3 possibility next hop will be ending at A. So which is why P of n is going to be 1/3 times Q of n minus Q of like n minus 1. So that's the first equation. And then Q of n is equal to, so which is basically the probability of ending at one of those not A's. So there are two cases in this case. You could either, like if your previous like hop was A, then you are going to be 100% ending at not A. Or if your previous hop was also another not A, that means you have 2/3 possibility you are still going to be ending at like this not A position. So which is why I will say 1 times P of n minus 1, which means if you were at like at position A, the state A in the previous like second, then you are going to be 100% at Q, which is not A. And or if you were at one of the previous like not A's, like if that was the case, then you have 2/3 possibility. Still, you are gonna be ending at one of those not A's, so which is why Q and -1. So if you are not convinced with these two equations, make sure you pause and make sure you kind of convince yourself before you move on. As soon as we have written these two equations, then we can just plug whatever we want to. So again, we know that if you were at like here, like time 0 before the first like hop, then after one hop, you are not going to be here at all. So which means it has to be P of 1 should be 0. This guy should be 0. And then you are going to be 100% at one of the other threes, which is not a position. And also another thing to remember, like Pn and Qn is add up to 1. So if you know this guy, you can just find in this immediately, or you can just plug into this equation to get these as well. I'm going to use that for the next ones. Okay, so let's say I'm going to find the P2, right? Which means what would be probable that we are going to be ending at this location after 2 hops. So P of 2, if you replace n is 2, so you will get 1/3 times Q1. So Q1 is this number, which is 1. If you multiply 1/3, so you will get 1/3. So which is why there is a 1/3 possibility that we are going to be back to the like state A. And if you want to plug the 2 for n to use this equation to get this second part, you can. But I'm going to use this guy because we know that their sum is add up to 1. If this is 1/3, so that should be 2/3. But for the sake of the confirming, I'm going to actually plug it anyway. So let's say Q of 2, right? So that should be P 2 minus 1 is 1 plus 2/3 times Q1. So the P1 was this guy, which is 0, and plus 2/3 times Q1. So Q1 is 1. So that should be equal to 2/3. As you see, this was actually what we got. So we can use the equation to get whatever we want, but as long as we have one of these, then the next one is easier to find it. So we just don't need that much work if you don't need to. So now if I want to find the P3, right? So if I want to write P3, so P3 is 1/3 times Q of n minus 1. N minus 1 is like going to be 2 because that's just one lesser. So that means that will be Q2. Q2 is equal to this guy, which is 2/3. If you multiply, you got 2/9. So that means this is 2/9. So to get this next Pn, you actually multiply the previous Qn minus 1 by 1/3 because that's what we have written. And then you can multiply now like the number right here to get 1 multiplied by 1/3 to get this one, but I don't know this yet. But I do know the sum of these two is 1. So if this is 2/9, so that means this is 7/9. And if I multiply this by 1/3, because that's what we just said, so that will be 7/27, and it will be 20/27. And we were interested in finding this guy. So the question was asking what would be probably after 4 hops that we are going to be returning back, right? So which is going to be 4, 7/27. That's it. So the reason I just like to use this approach, because if you are looking for maybe after 5 hops or like 6 hops, even 10 hops, you actually can use this approach, and then you can get that a bit way faster than the casework. And even faster, you can use the equation to actually find an explicit formula to find the nth like probability for any case. So without really going through each of these separately, but I'm going to leave that recursion stuff as your like exercise, and see if you can get that challenge and see if you can find another solution to this as well. Okay, so I hope that was clear. So again, if you kind of like more practice, please read the stuff in the resource in the description, and I'll see you in the next video.